A cell of electromotive force EMF 0.48 volts is connected to a metal wire X as shown in this figure. The cell has internal resistance and the current in the cell is 0.80 amperes. So here we can see that this is the circuit, and here this is the battery EMF, which has internal resistance, and there is a wire connected at the ends, and that wire has some resistance of 0.4 ohms. It has a length of 3 meters and a cross-sectional area of this. Also, the resistance is given. We are required to first compute the charge that passes through the cell in the time of 7.5 minutes. Now, we know it's pretty straightforward because we know that current is defined as the time rate of flow of charges, which gives me charge as current into time. Now, the current that is flowing is 0.80 amperes, and it takes 7.5 minutes. So 7.5 minutes. 1 minute is 60 seconds. So 60 seconds. This would give me the charge that flows as about 360 coulombs. So charge is 360. Next, we are required to calculate the percentage efficiency with which the cell supplies the power to the wire. So how efficiently is it providing that power? So to find the efficiency, we need to know the power that is supplied by the battery and the power that is dissipated in the wire, that is lost, whatever the spelling for dissipated is, in wire X, right? So we need to find out these two things, and then we can find the efficiency by, usually efficiency is represented with the symbol eta, the power lost over power supplied into 100%, right? So the power supplied is coming from the battery, the EMF. So we know that P is equal to VI, but for the battery, V is the EMF, E times I, and the EMF of the battery is given as 0.48 volts. So this would be 0.48 volts times the current, which is 0.80 amperes. So the power supplied is 0.384 watts. And the power dissipated in wire X is P equals VI. So the potential across this wire X and times the current that flows through it. We can rewrite this as V is equal to IR. So this is IR times I. So this becomes I squared R. Now we know both of these values. We know the current, that is 0.8 squared times the resistance, which is given in the question as 0.4 ohms. So this gives me the power that is lost in the wire is 0.256 watts. So the efficiency would be then 0.256 divided by 0.384 into 100%. And this gives you an efficiency of about 66.7%. There are 3.2 into 10 raised to power 22 free conduction electrons combined or contained in the volume of wire X. So this is the number of electrons, N. For wire X, calculate the number density, N, of free electrons, right? So we have to find the, by mistake, this is capital N, right? So this is the number of free electrons that are contained in the volume of X. The number density is this small n of the free electrons. So we know that the number density would mean it's a density of number, which would mean that usually density is defined as a quantity over volume, right? For masses, it's mass per unit volume. Number density is just number of electrons per unit volume contained in a volume. So we know that it's 3.2 into 10 raised to power 22 for N, and the volume can be figured out by multiplying the cross-sectional area with the length of the wire. So the cross-sectional area of the wire was also given 1.3 into 10 raised to power minus 7, and the length of the wire is 3.0 meters. So do the math, and this gives you 8.21 into 10 raised to power 28 per meter cube, which is 8.21 to 10 raised to power 28. Next, the average drift speed of the free electrons. Now, we want to find the average drift speed. We know that the average drift speed is given by I over N Q times A, where I is the current that flows, N is the number density, Q is the charge, and A is the cross-sectional area, which means that this would give me 0.80 divided by 8.21 into 10 raised to power 28 into 1.60 into 10 raised to power minus 19, which is the charge of an electron, right, of a free electron. And then you have 1.3 into 10 raised to power minus 7 as the area. So the math gives you 8 4.68 into 10 raised to power minus 4 meters per second. So that is the average drift speed of the electrons in the wire, the speed at which they are drifting. Now, here we have next part that says a wire Y has the same cross-sectional area as wire X. So there are two wires now, one is X and one is Y. Y has same cross-sectional area. And it is made up of the same metal. Wire Y is longer than X. So length of Y is greater than length of X. But the area and the metal is the same. If the metal is the same, that means the resistivity is the same. Wire X is in the circuit is now replaced by wire Y. Assume that wire Y has the same temperature as wire X, so temperature is also not changing. State and explain whether the average drift speed of the free electrons in the wire is greater than the same or less than that in the wire X. So we want to find now, compare the drift speed with now wire Y. Now resistance of wire Y would be greater than the resistance of wire X. Let's write it like this. Why? Because we know that R is equal to rho L by A. Now if Ly is greater than Lx, that would directly imply that Ry would be greater than Rx. So the resistance is high, which means that the current in the circuit will decrease. The current with wire Y will be less, or it will decrease. So if this current decreases, then we know that the drift speed, which was I over NQA, would decrease, right? Because the value of current is decreasing. So this would imply that the drift speed decreases.